Hello, thank you everyone for joining us for our webinar. This month, I am delighted to have Dr. Paul Hatzinger that's going to be speaking for us. I've worked with Paul for almost 20 years now, and plug your ears before I say this, Paul, but he is truly a brilliant scientist, one of the best that I've worked with. Love to hear his ideas, so I'm excited that you're going to be talking for us today on this. Quickly, for those of you that may not know Paul's background, he's the director of the Biotechnology Development and Applications Group at Aptum, and he has more than 25 years of experience in contaminant biodegradation, bioremediation, and forensics. His research group has really been instrumental in the development and field application of new remedial approaches for several key contaminants for the Department of Defense. Paul's done a lot of work on perchlorate, 1,2-dibromomethane, and NDMA. So Paul has extensive research on the application of CSIA to determine sources and fate of perchlorate as an example in the environment, and he maintains a strong interest in furthering the use of this in our environmental industry. So we're delighted to have Paul with us today. He has over 80 peer-reviewed papers, book chapters. He's been principal investigator on almost every grant agency that you can imagine. So we're thrilled to have you here today, Paul. And during the talk today, Paul's going to be walking us through how you can use stable isotopes to better understand the contaminant source and the fate of that contaminant. So many of you who have attended our webinars know that the webinar today is being recorded. It's going to be available on the resource section of the Microbial Insights website within the next week. Also, no need to contact us for that link. If you registered for this webinar, you're automatically going to get it. And you'll also get a survey that I'd like to ask you to fill out with just a couple questions about what your experience was. Now, at the end of the webinar this morning, there's going to be a question and answer period. So please type the questions for Paul into the software as we go along, and Paul will answer all of those, as many as we can, at the end of the webinar. If you have additional questions after we finish, you can always email Paul, or you can email us here at info@microbe.com so that we can get the answers from Paul and get back with you. So without further ado, Paul, I'll turn it over to you and let you tell us this big fish story you got going on here.
Thanks a lot, Dora. Thanks for the really nice introduction. Yeah, that's a photo from last summer. Nice striper in a kayak, which hopefully we'll get to again this summer. But onto the business at hand. So what I'd like to talk a little bit about today is CSIA, and I'd like to acknowledge the ESTCP program, who I've got a little bit of funding to talk about CSIA and try to promote this and get it used more widely in the industry. So a little bit about the webinar. I'm going to talk about some fundamentals first, and then I'm going to go through how we can use this technique to look at degradation or sources of chlorinated solvents. I'll then talk about some other contaminants of concern, 1,4-dioxane, which everybody's interested in these days, 1,2-dibromoethane, which unfortunately very few people are interested in, but it's an important contaminant, and then perchlorate. We'll sum up and then do a bit of Q&A. So CSIA, what can we do with CSIA? What kind of questions can we answer with this technique? First and foremost is my contaminant degrading in the field? Very important. Are its daughter products also degrading? Particularly with chlorinated solvents, cis-DCE stall or accumulation of vinyl chloride. Is that going away or not going away? What's the dominant degradation mechanism? Often by using multiple isotopes, you can get some idea of degradation mechanisms in the field. What are approximate rates? There's ways to use CSIA to estimate degradation rates apart from contaminant concentrations. And finally, is this actually my contaminant anyway? So there's a forensic aspect to CSIA. So just some fundamentals. What are isotopes? Well, isotopes of an element have the same number of protons and electrons, but a different number of neutrons. So we'll go back to 100 level chemistry, freshman year of college. These days, it's probably 8th grade chemistry. But anyway, so on our left here, we have a typical carbon atom. It has 6 protons and 6 electrons. Also has 6 neutrons, and that's by far the dominant isotopomer of carbon in the universe. but a very small percentage has one extra neutron, and this is called carbon-13. This is a stable isotope. It doesn't decay with time. There's another form of carbon, which is carbon-14, that I'm sure all of you are aware of. This is a radioactive isotope, and with stable isotope analysis, we're not talking about radioactive isotopes that decay over a period of time. So here are some environmentally relevant isotopes. So, you know, things that can be measured in laboratories. And if you look down this list from hydrogen, oxygen, carbon, chlorine, nitrogen, sulfur, you know, you'll recognize these as elements in a lot of the different contaminants that we're concerned about. Carbon, chlorine, and hydrogen are in all of our chlorinated solvents. You know, oxygen is part of things like MTBE and 1,4-dioxane. Nitrogen, explosives, RDX, HMX, a lot of different pesticides have nitrogen and or sulfur. The other thing you see from this slide is that the light isotope is typically by far the dominant species of those different elements. You know, usually greater than 99%. There's occasions such as with chlorine where it's less than that. Okay, so why are these things useful? I touched on this before, but what's important are ratios of these stable isotopes. And I'm going to talk a lot today about ratios rather than concentrations. And basically, depending on how something was formed or whether it's been degraded as a function of time, you have specific isotope ratios. So you can see there's a forensic aspect of this. If you have some chemical that's been made by different processes, often the isotope ratios in that chemical are going to be somewhat different. Secondly, in terms of documenting degradation, there's sort of a predictable increase in the ratio of heavy to light isotopes in lots of different compounds as they biodegrade and or abiotically degrade. So you can use this as a means to firmly establish that something's degrading in the field. How are isotopes measured? Well, they're measured with specialty instruments called isotope ratio mass spectrometers. These are not instruments that are very good at measuring chemical concentrations, but they're very good, they're very precise and very accurate in measuring these isotopic ratios. Now, you could take a sample from a groundwater well that has gasoline in it, and you could do isotopic analysis of carbon and hydrogen on that. That would be a bulk isotopic ratio. However, if you separate those compounds out first, so say you run GC and you separate out your benzene from your toluene, your xylenes, then you're going to get isotopic ratios that are compound specific. So for each chemical that you're looking at in that mixture, you're going to get an isotopic ratio. And this is really what defines CSIA, or compound specific isotope analysis. Now, this is often confusing for people, and it's how are these ratios reported? So they're generally reported relative to a known standard as something called a delta value. This Greek delta value, and this is something that's measured in ratios on a part per thousand scale, which is confusingly enough called per mil. So we know percent is parts per hundred, per mil is just parts per thousand. So typically, this delta value, in this case, this would be delta C13 in parts per thousand or per mil, is basically the isotopic ratio in your sample, so something that you sent into the lab, minus that in a standard. So for each of these different elements where isotopic ratios are calculated, there's a known standard that's used by all laboratories. It's an old fossil in this case, or something that simulates an old fossil called the PD belemnite. And then that's divided by the standard. And these are very, very small numbers. They're a couple points beyond the decimal place usually. So you multiply by 1,000. So I realize that seems complex, but basically through a lot of this, what I'll be saying is, okay, the delta C13 value is plus 30 per mil. Well, what does that mean? I mean, that basically means that my sample that I sent in has 30 parts per thousand, or a 3% higher ratio of the C13 to C12 relative to the isotopic standard. So basically, it's somewhat enriched, and you'll hear that term. It's enriched in the heavy isotope. This number can be positive or negative. So if your sample is lighter than the standard, this could be negative 30 per mil. So you'll see that that can go in sort of either direction. Okay, what becomes really important about all of this too is a process known as isotope fractionation. And basically these slight bond strength differences, there are slight bond strength differences between a heavy and a light, what's called an isotopolog. So here we're looking at TCE, and if that TCE molecule has a carbon 13, that's an isotopolog of TCE that has a carbon 13, usually bonded to a carbon 12. That's a very small percentage typically of those molecules, but also, you know, the bulk of those are ones that just have carbon 12 bonded to carbon 12 TCE. But what ends up happening often through either biological or abiotic processes is that as biodegradation occurs, and we see that happening here, we have sort of a high concentration of TCE. Here's our, let's say, our dihalococoides. It's degrading it to, in this case, cis DCE. As time goes by, what we see is our concentration is decreasing. The ratio of the carbon 13 to the carbon 12 TCE is increasing. This is called isotopic fractionation, or I'll also use the term isotopic enrichment. The other thing you'll notice here that becomes important is that for our daughter product, obviously the rate, let's assume it's not degrading. This is a cis DCE stall site, let's say. The cis is accumulating, but you can see isotopically it's much lighter than this TCE that started out. So we've got a heavier parent compound and a much lighter daughter product. And this is called a kinetic isotope effect. Now, a little bit heavier math here, but I just want to sort of illustrate this point a little bit further and introduce what's known as an enrichment factor, and I'll talk about that as we move along. But very simply, when you get these kinetic isotope effects, your TCE is degrading to a product in this case, and you've got two different rates. You've got a rate for those TCE molecules that have carbon 13, and another rate for those that have carbon 12. And this rate is going to be faster. So if you kind of look at those relative rates, we get what's known as an alpha value, which is a fractionation factor, ratio of the slower to the faster rate. And then we can kind of rearrange this to what's called an enrichment factor, which is 1,000 times this alpha minus 1. What's most important here is this enrichment factor is what we typically use to try and understand how much of this fractionation occurs during a biological process. And very frequently, this can be modeled by what's called the Rayleigh fractionation equation, or the Rayleigh equation. And this is the equation that brings together this delta value that I talked to you guys about at the beginning, so this measurement of isotopic ratios, with an enrichment factor and a measurement of how much of your contaminant is remaining. So if we take a look at, and that's F, this is the fraction remaining. So if we take a look at this figure from a paper, a fairly recent paper, and the references to all of these different figures that I show are in the back, and you're welcome to get a copy of this presentation at the end. But essentially what we see here is basically DCE is degrading. In this case, these are biological studies. So we have 100%, then 80, 60, 40. So the fraction is getting smaller and smaller as a function of time. And here we have our delta C13 value for DCA. We see in this process, and this is a biological degradation, dehalogenation pathway, isotopically we're getting heavier and heavier as the fraction of the compound gets smaller and smaller. So it's degrading as a function of time. Now, if we model this with the Rayleigh fractionation equation, the slope of this line, and if this was actually a natural log, this would be linear, but the slope of this line is this fractionation, or I'm sorry, enrichment factor, or epsilon value. So what you see here is a very strong enrichment, and the more negative this number is, the stronger that enrichment is. So if you see an epsilon of -30 per mil, which is, in this case, that's a very, very significant enrichment of isotopes as in this case, biodegradation occurs. The other reason I wanted to show this figure is because if we look at an oxidative pathway for DCE degradation, we see a very different scenario and much, much less enrichment. So this is only about -3 per mil. So what that tells you is, as this chemical is biodegrading in the field, you're getting very, very slight isotopic enrichment. So it may be that as you start to look at this may be very, very hard to to see in the field, whereas this hydrolytic pathway would be very, very easy to document in the field. Okay, so a little more about enrichment factors. They're best determined in a lab setting. For most of you practitioners, I'll show you places where you can find these enrichment factors in the literature. It's not something you're going to do on your own typically. They often vary among degradative mechanisms, as I just showed there, but are usually very consistent for the same mechanism. If you're in the field and you don't have fractionation or enrichment of at least 2 to 3 per mil, it's unlikely that isotope analysis is going to be particularly useful. Fortunately, a lot of processes fractionate chemicals to a much greater extent than that. You can get lower values in the field due to mixing and other factors, but still this can be very, very useful. And more isotopes are usually better. So the more isotopes that you can analyze for a given compound, the more data that you'll get in terms of your analysis. So where can you find epsilon values? Here's a couple of locations. One is a really good guide, and for those of you who want to follow up further on this, EPA put out a great document in 2008. It goes through assessing biodegradation and sources using CSIA. I refer back to that often. There's this ISOFRAC database, which was updated until about 2017. It's an Excel spreadsheet that you can download using this link. And it's very useful because it provides references and fractionation factors for, enrichment factors for lots of different compounds and different processes. And if we take a look at this is just part of that Excel sheet. This is an epsilon value. This is the compound. So this is degradation of cis-DCE. And we see using ZVI, so by abiotically, this is degrading, getting enrichment of around -20 per mil, which is great. I mean, that's a very strong enrichment, something you would clearly see in the field. And if we look down at reductive dehalogenation by a variety of different dehalococoides cultures or mixed cultures, we see a range, and this is not uncommon depending on what the experiment was, what the organism is, how these things were done. But again, very strong fractionation, and a fractionation that's similar in extent to that of abiotic degradation with ZVI. Now, the other reason I wanted to show this is if we look at co-metabolic degradation of cis-DCE, so this is aerobic degradation by organisms, in this case, that grow on toluene, we see only very, very slight fractionation. So in this case, if you were hypothesizing that your contaminant in the field was degrading aerobically, co-metabolically, you may look at this and say, wow, there's very little fractionation by this process. I'm probably not going to be able to see this in the field. This last set was interesting. These are a couple of organisms that grow on cis-DCE aerobically, and they also fractionate very strongly. Now, talking to Dora earlier, she also mentioned that for those of you that do isotopic analysis through Microbial Insights, and they do all of this, they have their own database that will allow you to look at these enrichment factors, and it's updated currently. So it's similar information to this ISOFRAC database, but runs right up through 2020, and they're happy to turn you on to that if you do your isotopic work with MI. Okay, so a little bit about CVOCs, protocol, strategy, talk about isotopic evidence of degradation and daughter product degradation. Then I'll finish up a little bit talking about sources in vapor intrusion and how you can maybe use CSIA to look at basically an indoor air source versus a vapor intrusion source. Okay, so how do I sample to do CSIA for CVOCs? The good thing is, for those of you who do field work or supervised field work, it's no different than sampling for 8260. Typical low flow, concentrations on the order of 5 micrograms per liter. Some of the labs, you can talk to the folks and see what they really need in terms of concentrations. Typically, you'll collect 6 preserved BOAs. You also need to collect samples for concentration analysis. The lab will typically want to know the concentration of each VOC in the different groundwater samples. There is no specific hold time, but labs, including MI, turn these around pretty quickly these days. This is a pretty routine analysis. Cost, it's on the order of $500 for the first compound for carbon-13. But if you have multiple compounds in a sample, so say you have TCE, cis, vinyl chloride, those second compounds tend to be relatively inexpensive. So you can run all of the different compounds you're interested in, the VOCs, usually from one sample. Chlorine analysis is a little bit more expensive, but again, it's the data that you can garner from that is often worth the cost. So which wells do I sample? Well, again, one of the points I want to make is this is not a panacea. This is not, I'm just going to go out to the field and do isotope sampling and it's going to tell me everything I need to know about my site. This is really a tool, and it's a tool that you use, on top of everything else that you typically do at a site. You need to understand geochemistry to determine mechanism. You need to have a good site model, groundwater flow rates, everything that we normally do. This just sort of adds some frosting to that, and sometimes provides information that can be very difficult from a lot of our, sort of routine analyses of concentration. But you can use this for M&A. You can sample along a groundwater flow path, as is in this case. You can sample the same wells over time. That's another method. You can use both strategies. But it's important to plan ahead. Again, it's relatively costly. So it's something where you just don't want to go out and sample a bunch of wells. You want to have a plan. You want to have a hypothesis about what you think is going on in the field and use this as a tool to help prove that hypothesis. One of the things that's really important to know when you do this is sort of the original range of isotopic ratios in your chemical. So, and I'll particularly focus here on PCE and TCE. So these are data from that 2008 EPA document. And essentially, what's important to know here is these are sort of starting material. So this is likely the isotopic ratio of the PCE or TCE that was dumped at your site 40 years ago. Here's sort of the mean, and here's the range among a variety of different samples. And I'll show you in a second why this is really important, because sometimes with this analysis, you get a snapshot in time, and just having some predictability about what the stable isotope ratio was of the compound that went in there can provide you with a lot of information. And here's a nice example of that. So here's a site. Basically, we have a couple of monitoring wells with really high concentrations. Maybe these are NAPLs. And you can see there's about a 10 per mil difference between these two wells. So maybe you'd say, could this be two different sources? That's certainly possible. But at a minimum, we say, okay, we know our starting C13 value was probably on the order of -23 to -35 per mil. We'll say -30 just as an average. And as we move down gradient, we see, we're starting to see isotopic enrichment, not so much in this zone from here to here, but as we start to look at these outliers, we see that the carbon isotope ratio is getting heavier and heavier and heavier as we move down gradient and as we get into some of these lower concentration areas. This is a clear indication that some type of degradation is going on at this site. And these values, both in terms of, you're flowing here, so there's a time factor here, obviously, but also all of these values are far heavier, so they're enriched isotopically compared to any of the original starting source materials. Now, if we look at the same plume with a different data set and make the same assumptions, this is basically what a data set might look like if you were just seeing dilution. So we have these two source areas, maybe NAPL areas. And what we're seeing here is mixing, and you can just do a simple arithmetic calculation based upon concentration and isotope ratio and show that, this is basically a 50-50 mixture. You can kind of show what sort of mixtures would occur if there's no degradation going on. There's always going to be some variability, but essentially what we see here is we've moved down gradient. We're seeing dilution. We're not really seeing any type of degradation here. And I've seen examples where people thought degradation was occurring by different processes. You had high concentrations going to low, and the isotopic ratios suggested, even though concentrations were declining, that it wasn't degradation that was going on. It may have been, wells placed in poor areas at some point in time that weren't capturing the whole plume. Now, how about daughter products? Everyone's always interested in daughter products. This cis-DCE and vinyl chloride, are they accumulating? Are they biodegrading? Well, you can use CSIA to take a look at that. And this can be a little more complicated. And but again, I'll give you sort of a metric to use. In this case, for daughter products, in this case, let's just assume this is TCE going to cis-DCE, and there's no further degradation occurring of the cis-DCE. As my TCE biodegrades, it gets heavier, starting at -30 per mil. The problem is that the daughter product that's being produced from that is also going to get heavier, right? Just naturally, because this is being enriched, so the daughter's also being enriched. And you'll get to a point in time where the TCE in this case is completely gone, and all of the cis-DCE is now at -30 per mil. So TCE is gone, your cis is -30, if it's not biodegrading. So that's the important point. That daughter product will never get heavier than the original parent if it's not biodegrading. So you'll never see cis above that about -30 per mil metric if you're sampling out in the field. Now, the other scenario, if they're both biodegrading, so the parent, the TCE is biodegrading and the cis is biodegrading, you can get values of cis that are much, much heavier, so much more isotopically enriched than this -30 per mil. And this in itself is a clear sign that biodegradation is occurring. Now, of course, you know, you can add some complexity here because you may have both vinyl chloride, which would be down here, or ethene. But interestingly, if you have a complete mass balance at your site, so if you know, you can see this in microcosms or pure culture studies, if you have all of your TCE, your cis, your vinyl chloride, and your ethene, and you add all of those up, concentration and isotopic ratio, at each point in time, that'll be -30 per mil. So that will be, if they're all added, they'll be heavier, lighter, but they'll all ultimately add up to -30 per mil. Okay, so let me just give you an example of a degrading parent and daughter product, and this is just a this is Raritan Arsenal, and essentially there was some work done here. It was biodegradation work. Emulsified oils were injected. There was also a research system put in at points in time, and this was some work that was ESTCP funded, as I'll show you in a minute. And it was essentially going back to some of these sites and trying to see if we could use modern tools, including CSIA, molecular tools, passive flux meters, and understand what was going on at these sites and whether bioremediation was truly effective several years later. So were organisms still there? Was degradation still occurring? And this just happened to be a plume that hadn't been sampled in several years. But essentially, there was still a little bit of TCE and a little bit of cis left. So what was done here is that sampling was done along a groundwater flow path and looking at both concentrations of parent and daughter, as well as isotopic analysis of parent and daughter products. And here are what those data look like. So this is the TCE plume in this case. There was very little left, you know, a few micrograms per liter. But the thing we see as we move down gradient, these are the isotopic values. First of all, that most concentrated well, sort of up in this range, is isotopically much heavier than our presumed starting TCE, or any of the sources, which ended up around -23 per mil, let's say. And as we move down gradient, we're seeing isotopic enrichment. And you can see this is done with very low concentrations of TCE. As we move to cis, you remember that example I gave a minute ago? Let's first look at what our isotope ratios are in the cis, or our delta values, -8.2 per mil. That is much, much heavier than starting source material for TCE, so that clearly indicates biodegradation of cis-DCE occurring. As we move down gradient, and these are actual isotope data, we see, okay, we're sort of about the same in these two zones. You know, even though this concentration has dropped a lot, suggests there maybe isn't much degradation going on here. But as we move along the flow path, again, a little bit of an odd point here. It's a little bit lighter. But as we get down further, we see that as we're getting to the very end of the cis-DCE plume, we've got dramatic enrichment. You know, so potentially what's going on here is maybe there's nothing anaerobic going on, but we're starting to see some, you know, some co-metabolic degradation further down in the plume, something along those lines. So, you know, there's or it's or it's just again reductive process that's just occurring down in this zone a little bit more prevalently. Okay, so can we do anything with rates with this information? And the fact is we can. And again, with good data sets, and I'm going to refer back again to that EPA document, and John Wilson and others were a part of that, but that provides a means to basically estimate rates. It's a little different than this, but fairly similar. But I just wanted to show you making some assumptions that you can use isotope values along the flow path, essentially to estimate degradation rates independent of chemical concentration. So in this case, what we're doing is we're just assuming a first order rate, and this is what we're trying to solve for is a degradation rate. We have to assume a seepage velocity, but of course, if you have a good model, you can estimate that. And an enrichment factor, and you can play with this with a range of enrichment factors. In this case, we assume -15 per mil, and that's going to be fairly conservative. As I showed you before, with if we assume this is reductive dehalogenation going on, we had enrichment factors up to -25 per mil. So essentially what we do is we plot this out. We plot out a delta value as a function of distance. And of course, this then also becomes a time function, because if we make our 2 feet per day assumption, we sort of know what our time is along this flow path. And here's a plot for TCE, and here's a real world plot for CIS. And yeah, the R-squared value isn't great, but again, we're doing a rate estimation. And basically, by solving this, you can get a K value and a half-life. So in this case, for TCE, looked like it was about 80 days, and DCE about 30 days. And again, with more data, or as a function of time, these data sets can potentially tighten up a little bit. But the great thing is this is a means to do this independently of concentration data. And clearly, this is degradation going on, right? Because you're getting isotopic enrichment. Okay, so I'm going to sort of end there with groundwater VOCs and move a little bit into indoor source areas or vapor intrusion. And there was a very nice study done by GSI, Tom McHugh, along with Tomas Cooter and Philip at Oklahoma. And essentially, they wanted to take a look at whether you could actually distinguish PCEs from an indoor air source versus a vapor intrusion source from groundwater. And you'll say, well, are there still CVOCs and products? And yes, there are. So, if you're home cleaning your gun, you pepper spray somebody, or you're a big hobby modeler, putting together model airplanes, you may very well have some VOCs in your household. And perhaps that indoor air source is a local source rather than the TCE plume that's, been flowing under your property in New Jersey for the past 50 years. But there's a means to use CSIA to try and understand that. And the kind of the neat trick here is this is sort of a pattern matching exercise. And essentially what these guys did is they said, okay, again, we know the range for manufactured sources of different chlorinated solvents. We know what the delta values are typically for chlorine. They're in this range. We know the values for carbon. And this is what's called now a dual isotope plot. So any recently manufactured or previously manufactured VOC that's not been fractionated, that's not been degraded in any way, should fall within this range. Now, in the subsurface, if you've had degradation going on, so there's been isotopic fractionation, that's really what this depends on, then that original carbon and chlorine delta value has become enriched with time, and it's likely moved out beyond this original range for manufactured sources. So essentially, the idea here is you take an indoor air sample and you basically compare those data, both carbon and chlorine isotope values, to manufactured sources versus the source in the groundwater that's potentially fractionated. And here's basically some of the things you might see. So here's our range, here's our indoor air sample, here's our groundwater sample. So here's a perfect example of the indoor air source being a modern, gun cleaning product or something along those lines, because you can see this is not matching what you're finding in the groundwater, which is highly fractionated. Here's the reverse example. This is a vapor intrusion example. So Basically, the isotopic value that you're seeing in your indoor air source is very close to what you're seeing in the groundwater. And here would be a mixing scenario where you're somewhere in between. So maybe you have a little bit of an indoor source and you also have groundwater vapor intrusion source. And again, this just happens to be Raritan Arsenal again. And this was an example used in that ESTCP project where they actually went and did this type of sampling. And it worked really well in this case. They took samples from within the building. They took samples from along the plume. So here we see the plume TCE samples were highly fractionated, so they're outside of this curve of parent sources, but all the indoor air sources were right down in this range. So basically your conclusion from this is in fact that indoor air source of TCE at this site is something modern. It's something that's being used in the facility. It's not coming from the groundwater source. So that sort of wraps up everything that I wanted to talk about with VOCs. And then I'm going to do some kind of finish out here today before Q&A. I'm going to do some sort of smaller sections on some different compounds that may be of interest and how CSIA can be used either to document their degradation in the case of dioxane and dibromoethane, or to look at sources in the case of perchlorate. So I'm sure a lot of you out there have dealt with or soon will be dealing with 1,4-dioxane. It's basically, it was a stabilizer in TCA, trichloroethane, but it's also found at a lot of TCE sites. It's not completely clear whether it was used in TCE. Some will say it wasn't. Some will say it was. Some will say it wasn't. Either way, if you have a TCA or a TCE site, you really should sample for 1,4-dioxane. It's miscible in water. It doesn't sorb well to carbon. It doesn't strip well. You typically see ppb concentrations. It's a probable carcinogen, but it is biodegradable. The problem is it's not biodegradable in the means that we normally use to degrade chlorinated solvents, which is adding carbon sources and making everything very anaerobic. For the most part, the biodegradation literature on 1,4-dioxane suggests that either there's a small subset of organisms that can grow on it aerobically. The one term CB1190 is one that many of you may have heard of. And there's a lot of organisms that can degrade it co-metabolically, meaning these organisms use some type of primary substrate, propane, ethane, in this case tetrahydrofuran. They grow on that. And then these enzymes that allow them to grow on that just fortuitously break down 1,4-dioxane. And that's the sort of the typical co-metabolism which occurs for lots of different compounds. Now, a really interesting study was done a few years ago by Dave Adamson and Chuck Newell at CSI, along with Hunter Anderson at the Air Force and Shaylee Mahendra at UCLA. And essentially, they went and they used a database at a variety of different sites, and they look at half-lives of 1,4-dioxane, not using CSIA in this case, but just using concentration and site models. And what they found was, for a number of these different sites, it appeared that half-lives were on the order of a few to several years, and for others, it was 10 years or more. But the fact that you were seeing fairly short half-lives was pretty interesting, suggests some M&A going on potentially at these sites. And the other thing they saw, let me just back up here. The other thing they saw was that there was a positive correlation with dissolved oxygen, which would indicate potentially either a co-metabolic pathway may be going on, linked to ethane or ethene or other substrates that are produced at sites. Maybe when you add emulsified oil to treat a chlorinated solvent, and that emulsified oil degrades, and if your chlorinated solvent degrades, you produce some ethane or ethene, and that moves down gradient, then maybe what you have is now co-metabolic degradation of 1,4-D. Or maybe you have some of these type of organisms that can grow on it occurring again as that starts to remix with the groundwater and you see degradation. And the fact that this was inversely correlated to metals and CVOCs, which can be toxic to these types of organisms, particularly 1,1-DCA is a very bad actor, which forms from hydrolysis of 1,1,1-TCA at TCA sites, then that again suggests maybe there's an M&A aspect of this that's going on at a number of these sites. But how do we document that? I mean, it's very difficult. We don't have daughter products for 1,4-dioxane that are easily measurable. So the answer to that in the future and the near future may be dual isotope analysis of 1,4-D. This was some CERTA-funded work, and it's led by Peter Bennett, and he's teamed up with some folks at Waterloo, Ramon Aravena, and others. And essentially, they've developed a technique where you can look at hydrogen and carbon isotopes in 1,4-dioxane. And what they've seen, and there's not a lot of data at this point, but I'm sure there's more coming, is that you get a small to moderate carbon fractionation, so 2 to 5 per mil, and a relatively large hydrogen isotope fractionation. There's always more variability associated with hydrogen isotopes, but again, so dual isotope analysis may become very useful, particularly for M&A evaluations of 1,4-dioxane biodegradation in the field. And I was just going to show you this. This is a paper that they published, which is in the reference list. But essentially, you had a couple of co-metabolic organisms that grow on propane and isobutane. I think this was done in Mike Hyman's lab. But essentially, you can see that they fractionated carbon to almost exactly the same extent, very close on hydrogen. And this is basically, people will often look at ratios of these fractionation factors. And these, as I mentioned before, you get a lot more variability with analysis of hydrogen isotopes. But again, these are in the same range. But interestingly, if we look at this other organism, it grows on tetrahydrofuran, it's probably using a different co-metabolic enzyme than these, and it fractionates to a much greater extent, about 5 per mil and 150 per mil for hydrogen. So again, this also starts to point toward different mechanisms of degradation, potentially enzymatic mechanisms, different points where the molecules attack, something along those lines. And that's sometimes what you can gather from this type of isotopic analysis. So look for that in the future. Okay, so the next compound I wanted to touch on is dibromoethane, or EDB. It's more forgotten than emerging. It was a fumigant used in the 80s. It was used in leaded fuels, and it's still in avgas as a lead scavenger. It's also a pretty well-known carcinogen. EPA's had an MCL for this compound of 50 parts per trillion since, I believe, 1990. And yet, I'm not sure how many of you have EDB sites. I suspect it's not a lot of you. So is that because it's not there? No, that's not because it's not there. It basically occurs widely in groundwater above the MCL, again, of 50 parts per trillion. Part of the problem is it's not detected down to those concentrations by EPA 8260. But if you look at some work that Ron Falta did and EPA did a number of years ago, they went back to old underground storage tank sites, many of which were closed for contamination with petroleum hydrocarbons, measured EDB. So here's the concentration in wells at those sites. Here's the MCL. So anything in this range is exceeding the MCL at the site, often by orders of magnitude. So in this case, if we look at South Carolina data, 30% of the sites, exceeded the MCL by 20-fold. And I mean, look at the concentration. It's very widely occurring. Here's here are the sites that were exceedances. But it's not something we worry about particularly. I think that's a philosophical question at some point more than anything as we come into this PFAS world. But is it biodegradable? Yeah. Aerobically, anaerobically, it can be biodegraded. It's also degraded abiotically. So there's a lot of means by which this can break down. So here are laboratory determined enrichment factors. So as I mentioned, these should be done in the lab. This was done by Paul Koester-Van Groes at Aptum, and the data were analyzed by Tomas Kuder at Oklahoma. This was published recently. But essentially what we see, here's anaerobic biodegradation of EDB. These are a bunch of cultures that are mixed cultures that contain dihalococoides. They all fractionated about -8 per mil, which is a decent value. Oddly, there was one culture which came from Colorado. Again, it's a mixed dehalogenating culture which fractionated to a much greater extent. Suggests, again, maybe a different organism in that culture, a different mechanism. Here are a couple of aerobic organisms. This one grows on ethane or propane. You can see it fractionates about -6 per mil. Methylacella is a methanotrope, grows aerobically on methane, fractionates at about -3 per mil. So you can just see here again some of the differences in fractionation factors based upon different processes. And here we have iron minerals, a couple different iron sulfides, fractionate very strongly, but a little bit differently. And then the other thing with EDB is it hydrolyzes slowly with time and water. And you can see, this is just done at different temperatures, but essentially very good fractionation with hydrolysis. So I guess that's the good news, is this compound is always hydrolyzing over time, although the rates can be relatively slow. I'm just going to show you quickly a case study. This is EDB at Kirtland Air Force Base near Albuquerque. There's a big plume there from an old avgas fuel spill. It's very deep here, 500 feet to water. There's still napple up in this area, and we've got more than a mile-long plume flowing under some neighborhoods. And again, this plume is also so large because this is the 50 part per trillion contour. These are very low concentration. But there was a lot of debate at one time about whether there was degradation going on of EDB in this plume. Could that be documented? And through an ESTCP project, CSIA was done, and that data set is one of the nicer ones that I've seen for a compound like this. And we see, again, here we are in the source area. We've got negative delta values in the source area. And then as we start to move down gradient, we get up into the range of positive 40 to positive 60. So you clearly see isotopic enrichment moving down gradient. Now, one of the things that's interesting, if we move over to the figure, we don't see a lot of isotopic enrichment in the original source area where there's presumably still napple. Now, part of the reason for that may be, and this is something to think about with CSIA, if you have a napple remaining, as biodegradation occurs, you're often going to get repartitioning of the compound with its original isotopic signature out of the napple. So this may skew your interpretation of the data a bit because it says, well, maybe degradation isn't going on here, or degradation is going on. And in fact, what's happening is you're getting repartitioning. So you're always getting a resupply of basically of a lighter version of that. Now, as we kind of leave the napple area, sort of into this zone, we start to get strong isotopic enrichment. And then as we get way down gradient into the aerobic zone, we see continued fractionation as a function of distance. And this shift is almost matches perfectly with hydrolysis. So this shows you not only that degradation is occurring, but it also starts to indicate a bit about mechanism. But if nothing else, this clearly shows that there's attenuation of the plume is occurring at the Kirtland site. So I'm going to take the last 5 minutes before Q&A and just finish up and talk a bit about perchlorate. And this is a forensic means to look at perchlorate sources. For those of you who aren't old enough, that's a space shuttle, and what propelled that thing into space was the largest rocket motors ever built, at least at the time, and they contained about 700,000 pounds apiece of ammonium perchlorate as an oxidant with solid aluminum as a fuel source. And 25 years ago, people started to think that this was a problem at some military sites, but it seemed to be a very limited issue because there was only certain sites that really used this, rocket testing, NASA facilities, hog out facilities, a few commercial sites. And then the EPA started requiring further testing. And what they found was in low concentrations, they detected perchlorate all over the place. So the question is, are there other sources? And the answer to that is definitely. One is other synthetic sources, fireworks, flares, perchloric acid, bleach has perchlorate. So that could be, a source in some locations. But interestingly, for many, many decades, and even today you can still buy these products, but along coastal Chile is the Atacama Desert, which is one of the driest places on Earth. And there's a caliche material there that's super rich in nitrate. And if you look at this photo, this is Andrew Jackson from Texas Tech and some of his crew. You can see how, you're really not going to want to farm here in the Atacama. Caliche deposits, these are salts, they're enriched in nitrate. And basically those were processed primarily for fertilizers and for use in explosives beginning in the 1800s. And a battle called the War of the Pacific was fought between Chile and Bolivia and Peru to basically gain access to this Atacama resource. And this was also the first naval battle of World War I between England and Germany was fought over this resource as a source of nitrate for explosives. So really interesting. But importantly, a lot of this was imported into the United States as a natural nitrogen fertilizer for citrus and lots of other crops. Perchlorate is also naturally formed in the atmosphere, and in places that are very arid, it can accumulate in the soil and then get pushed down as irrigation occurs, so it can get mobilized. So I think if you go back 10 years, no one really thought these natural sources of perchlorate contributed to contamination. Through CERTIP and ESTCP funding, isotope methods were developed to measure chlorine and oxygen in perchlorate. And in part, this was done by collecting large volumes of groundwater on small ion exchange columns and then purifying the perchlorate and running analyses. And if you started looking at sources, and again, this is another dual isotope plot, oxygen versus chlorine, what you see is that all of this material from Chile, and these are just caliche, the blue is just caliche samples, whereas the green are actual fertilizer, historical fertilizer samples. The chlorine in these is much, much lighter than you see in any of the synthetic perchlorates. The oxygen overlaps a bit, but again, if we use dual isotope analysis, we get these sort of distinct ranges where these chemicals occur isotopically. And the material that was collected from the southern high plains, so Texas and New Mexico, as well as Death Valley, has its own area. And so it seems to isotopically be distinct from either the Chilean or synthetic material. So we have potentially different source terms. And just kind of my last example here, which is really interesting, this is Rialto, California. There were 2 synthetic plumes of perchlorate in Rialto, the Mid-Valley and the 160-acre site. And then the question became, they started finding perchlorate down here to the southeast, across a couple of faults, down to the southwest. And the question is, what's the source of that? They kind of understood the flow here, but had this perchlorate impacted these wells? Had it somehow crossed the fault? And if we look at this interesting plume map, this is the direction of groundwater flow. We see that in this map, this plume went all the way down through the Fontana area into the Chino subbasin because they were seeing concentrations here. So they sort of drew the plume map down here. So the question is, what is this? Is this perchlorate synthetic from these plumes, or is it something else? So a lot of isotopic work was done, sampling by USGS, and Neil Spirchio did the isotope work out of Delaware. J.K. Balke at USGS did oxygen work. But basically, this data set showed, everything in here in red along these plumes models of synthetic perchlorate based upon the isotopes. And here are the actual points in red in the synthetic perchlorate in the background. But all of this material to the southeast, all of this material to the southwest groups almost perfectly with this Atacama Chilean material. And these were historically orange groves or vegetable growing areas. So what you have here is a legacy of Atacama type perchlorate down in these zones that contaminates groundwater from former fertilizers. And we've seen this at sites in Long Island and other areas as well. So this is not uncommon in former agricultural areas. So I'm going to wrap up right here and basically just say there's a lot of benefits to this. Provides direct evidence of attenuation, can be used for generating rates by different means. You can identify sources of some contaminants. It's commercially available for a lot of compounds, including VOCs and 1,4-dioxane. Some limitations: you need relevant fractionation factors. The data are rarely ideal. You need interpretation. You need to understand your site and what you're really looking for. And it, again, should always be evaluated with relevant geochemical, hydrological, and microbiological data. I'll wrap it up there. If there's any questions, please go ahead. So Dora, were you going to ask some questions, or should I?
Yeah, sorry, Paul, I couldn't get my mute off.
No worries. No worries.
Doesn't help to talk on mute. Okay, so we do have a lot of questions. So everyone, we'll get through as many of these questions as we can over the next 10 to 15 minutes. If you want to stick around with us for a little bit, and then whatever we can't answer, I'll get with Paul and we'll create a document that can be sent out to everyone that's attending. So the first question we have, Paul, is there anyone that's using chlorine isotopes? And can you talk a little bit about how those are being used?
Yeah, for sure. So the commercial labs these days, you can get chlorine isotope analysis done commercially. If it's unusual compounds, Neil Sturcio, I think, originally developed the method. He's at Delaware now. He developed the method for perchlorate, and I think an original method for VOCs. But commercial labs do run both carbon and chlorine. Waterloo runs chlorine, and it can be used a lot like carbon. And as I mentioned, again, if you're talking about VOCs, if you're looking at other compounds, I showed you the importance of it for perchlorate isotope analysis, but, you can use it like you can with carbon, and often it's worth doing both carbon and chlorine. There are some instances where if you look at those relevant fractionation factors, you might be able to discern different mechanisms if you're interested in that, when you're using dual isotopes, so carbon and chlorine combined for VOCs.
Okay, what do you think about multiple sampling events? How many do you think that you need over time to really be able to examine enrichment factors?
Yeah, I think that's really gonna depend on your estimated rates, and probably what you should do is get your model or engineer to try and estimate what you're going to see. So make some of those same assumptions that I made on that little figure where, okay, here's groundwater flow, and let's say you're doing this, as a function of time. If you don't have another source that's contributing, so you don't have a NAPL area that's going to confound this, you just have dissolved phase, presumably biodegrading or abiotically degrading, then estimate a rate. Is your half-life on the order of weeks or days or years? And then by using fractionation factors, which you can get from the literature, you can say, okay, if in fact my degradation rate is what I think it is, then I should see an isotopic enrichment of X per mil, and you can model this pretty simply. I should see an enrichment of X per mil over this period of time. So, if you think it's really quick, obviously you're going to want to have sampling events closer together. If you think it's a very slow natural attenuation process, for instance, you're going to want to be further apart. But you should be able to if you can come up with an estimate and say, geez, I think the half-life of this is probably on the order of 6 months or a year, then you can probably determine your sampling schedule and what that isotope value should be in the range of when you do collect that sample a year later, if in fact the degradation is occurring at the rate you think it is.
Okay, great. I know this varies depending on the CVOC, but can you talk a little bit about the lowest concentrations for some compounds that we can measure?
Yeah, so it really depends on, and I'll give you an example. So for EDB, we're interested in dibromoethane down in the tens of part per trillion range. So in order, and isotopically, you can actually measure EDB at those concentrations, but what you need to do is do like a solid phase extraction on the sample. So, and Tomas Kuder at Oklahoma, for the data I showed, basically worked that out, where he developed a method where he could see down in that range of interest, which was really down in the 50 part per trillion range or lower, by concentrating samples that were sent. And he also worked out a method where, when he was in a complex matrix, when you have a lot of these other compounds around, you have NAPL, that really becomes a messy sample, and you have to be very sure that you're not getting an interference of another carbon compound, because if you are, that's going to skew your isotope results. So you have to be sure that that's all cleaned up in order to do that. So that's just one example of where, you know, an academic lab did that. But for other compounds, I'm sure you can do the same thing. You know, for a typical CVOC site, I think you're basically on the order of 2 to 5 ppb for a lot of the different compounds that you'd be concerned about. TCE, PCE, cis and vinyl, for instance, should be in the same range for some of the chlorinated ethanes or methanes in order to, you know, to determine those delta values. But again, if it's, you know, if you really need to see something at an ultra low level, then it's certainly possible to work with a lab and do some extraction, solid phase or otherwise, to concentrate those compounds. The only thing you have to be sure of is you don't fractionate the chemical when you do the extraction procedure. So you have to make sure, you know, you have to run some controls to say, okay, I can concentrate this chemical, but in doing so, I'm not changing the isotope ratio. But, you know, you can do this at pretty low concentrations for a lot of these VOCs.
Great. Have you seen CSIA used for TBA? The question is that the literature seems to be mixed for aerobic and anaerobic degradation mechanisms.
That's yeah, I'll have to look into that. I mean, certainly, I know that this has been done pretty extensively for MTBE, right? Which MTBE, the first daughter product of that is TBA, typically through aerobic degradation. And there's some nice examples of MTBE work in the 2008 EPA document on CSIA. I think they use that as an example of looking at degradation of a chemical. So that being said, I'm not familiar with TBA literature, but I would expect that there'd be no reason that you couldn't do carbon isotopes and probably oxygen isotopes on TBA. I'd be happy to sort of take a look into that, Dora, if you want to shoot me the question and respond further by email, send some papers if I can track a few down.
Okay, that sounds great. I'll do that. One of the questions is about preservation. So when we collect the samples and we say that we need to preserve them and chill at 4 degrees, but then we say that there's no hold time. Can you talk a little bit about that?
I can. So when I said no hold time, what I really meant was there's no, and this is a local issue, meaning that there's no established sort of EPA methods like there is for 8260, where it clearly defines, you know, preservation conditions and hold time. You don't have those same sort of clear guidelines with CSIA. Doesn't mean, you know, you want to save a sample for 50 years, but essentially what I meant there is what you really need to do is talk to your isotope lab and just kind of look at their schedule. But there are times when, you know, the labs, either because of backlog or whatever, can't do this as quickly as you can run an 8260. So, you know, you may not get your data. It may take a little bit longer than, you know, than a typical sort of a hold time for those compounds. Should you try to do it within the established EPA hold time to determine concentration? Sure, you should. But, you know, sometimes you're you know, the labs that do that can't, you know, can't always do that. I mean, that's kind of what I was getting at there, is that there isn't for most of these methods, you know, there aren't really, there's guidelines, but there really aren't, you know, established procedures that you have to follow like there are when you're determining chemical concentrations of most things by standard methods.
Well, and I think one thing that's important to point out too is that with an 8260, you're worried about volatilization over time or escape. That doesn't affect CSIA since we're not impacting those isotopic ratios. So even if the concentration changes due to volatilization, we should have the same isotopic ratio, which will give you the same data.
Right. Yep. And I think, Dora, too, I mean, I think the time frame has gotten shorter. More labs do this. I know you guys do that. I mean, we've used your lab, and we often have data turned around easily within 2 weeks.
Yeah, most of the time we do a goal and we try to run it as quickly as we get it. So sometimes the delay is more in processing the report than actually running the samples. It gets on the instrument very quickly. But we try for 2 to 3 weeks, worst case, on especially on the carbon. The carbon's usually 2 weeks or less.
Yep.
Okay, so one question is, what can you do if you have two samples from an area, but it's only a single time frame?
Yeah, so in that case, I think, and this happens a lot, right? You have a snapshot in time. That's where knowing sort of the range of what the parent material was, the isotopic range of the parent material, and I showed the one figure where it just showed the different VOCs, and I assume this is VOCs. It could, if it's something else, just let me know. But basically, if you look at that parent and it says, okay, the range of the delta C13 range from -25 to -35, and all of the samples that were tested, all of the source samples historically that were tested, and my sample at this site is +15, that's just a clear indication that there's been degradation of that compound. If you have two locations and one is +15 per mil and the other is -30 per mil, then you might indicate that either you've got a NAPL situation. Again, you'd have to really understand what the site conditions are, or there's no degradation going on in one area and a lot going on in another. But that's kind of all you can do, with that snapshot with a few samples at one point in time, is look at what you thought the parent was. And there's rare occasions where, if you have a bunch of undegraded NAPL, you might be able to get a parent signature, or certainly a signature in a NAPL that's contributing to the plume. And you just have to it's kind of, a broad brush at that point, saying, yes, degradation's going on, or no, it's not. Or it's inconclusive if, again, you have a situation where, you're right on that fringe of the parent source isotopic values.
Great. All right. The next question is, can forensics be used for contaminated soil? And if you had a new spill versus an old spill, would you be able to differentiate those?
Well, yeah, that's an interesting question. You can do this, so you can extract solvents from a soil, and you should be able to do CSIA that way. I'm not as familiar with that, but we've extracted perchlorate from BETOs from unsaturated soils and done CSIA work. I don't see why you can't do that with chlorinated solvents. I presume you certainly can. Now, in terms of the forensics, this gets confusing when you're talking about chlorinated solvents. I mean, clearly when I showed you those parent ratios, if we just look at TCE, the parents range from -23 to -35 per mil in terms of carbon. And there's less chlorine data, but there's also some chlorine data that you can look at there. And if you're going to do this, I would certainly do at least dual isotopes. But the question is, do you know historically sort of what contaminant went in? And that's what can be problematic, because if you're at a vapor degreaser somewhere, you probably had over many years different sources of TCE coming in that had a slightly different range, and now you're somewhere in the range, but you don't know where you are. Now, that being said, if you have an old spill that's been biodegrading as a function of time, then it may very well be fractionated. So it may be much, much heavier than another area where you have a more current spill. So you may be able to distinguish those two sources just because one is highly fractionated and one isn't, which is a lot like the vapor intrusion example that I showed. I mean, I don't see why that couldn't also be practical for a soil example as well. And I guess the other thing is, if you have spills in a couple of different areas, and that they can't commingle, and in the soil, perhaps that's the case, it might be worth sampling both just to see if there's a local difference. So if in one area your isotopic ratio is -25 or 24 per mil pretty consistently, and it's -35 in the other area, that de facto is an indication that those are different sources if there's no way that they, could have commingled with one another. So it's probably worth a shot because there's enough range in these ratios that at a local site, you might be able to distinguish two sources.
That's great. Okay, so Paul, we have probably at least 30 more questions that have come in. I know we won't have time to get to them all today. Would it be okay if I put these in a document and we can work together to answer everyone's questions and then send that out to people? Would that be okay with you?
Yeah, absolutely, Dora. Absolutely.
I think there's a lot of good questions in here. So everyone, if your question didn't get answered, I'm only going to ask one more of Paul before we end today. But if we didn't get to your questions, there are a lot of really good ones in this. We will put together a summary document with Paul's responses, and we will send that as an attachment out to everyone that registered for the webinar. So you'll get all of your answers. And then if you have additional questions, you can always email us at info@microbe.com or reach out directly to Paul, and we'll be happy to talk to you. Okay, so one last one for you, Paul, and I think this is a good one. How much fractionation do you need for chlorine and hydrogen? I know the EPA says 2 per mil for carbon. Is it the same for those, or is there a difference?
Yeah, there's definitely going to be a difference. I would say you're going to be in about the same range for chlorine, but it's going to have to be a lot higher typically for hydrogen, just because the variability is such a small molecule, and the variability in just in your routine analysis for that is very, very high comparatively. So, for carbon and chlorine, your lab, you're basically your lab variability is probably on the order of, 0.5 per mil, something in that range. It's much, much higher than that for hydrogen, probably maybe even an order of magnitude higher, depending on, it may be 2 to 5 per mil or greater. So yeah, I mean, just based upon that alone, you're going to have to see much more hydrogen fractionation than you are either carbon or chlorine in order to have a, sort of an accurate result.
Okay, that's great information. Yeah. I think that that's something that we'll kind of notate in the sheet too when we send out, because I think that's really important for people when it comes to interpretation.
Yeah, great. I'm sorry there weren't any PFAS questions, Dora.
Yeah, I'm there. Well, I haven't gotten through reading all of them because they keep coming in. So maybe there are. I know there's a lot about the perchlorate. Oh, there is a PFAS one. So we will answer that one. Hold tight, it'll be coming back to everyone. So
Right.
but thank you again, Paul, as always. I love hearing you speak. Wonderful presentation, I think very informative. And thank you everyone for attending. We really appreciate it. Know that you're all busy, especially during this difficult time, so we appreciate you sitting in and listening to this webinar. And again, we want to be there and be helpful for you. So reach out to us at info@microbe.com or to Paul, and we will be happy to answer any of the questions. And thank you again, Paul, for being here today.
Yeah, thank you, Dora. And thanks to everyone who took some time to listen also. Much appreciated. And I hope some of it was useful. Thank you.
All right. Thanks, Paul. Bye-bye.
Bye-bye.